Okay, so we will start the second session on ITK. We started yesterday, hopefully installing and running the Hello World example. All right? So today, well, first I would like to check if everybody has been able to download, install ITK and run the Hello World example, and then if everything works, then we'll move forward with doing some examples on input, output, and filtering. Okay? That will be the idea of today's class. Everybody has been able to run Hello World? Yes? Yes? Who hasn't? Let's ask this. Who hasn't? So everybody's fine with compiling, running it, and all these things? Yes? Okay. You're good. All right, so today we are going to work with some images. The images, the examples, and everything is the same link in the Google Drive directory as yesterday. In case you don't have it, it's this one. Okay, well, you have it in the... No. If you download the PDF, it's in this. It's already in the same place as yesterday. Okay. If we click on this, it will go. Well, this is my directory. Well, you'll see something like this, probably. I don't know if you see it. Probably now. You should have Hello World, that is the one we did yesterday. Okay. Software is still the same. Tutorials, you have PDFs coming from ITK itself, so in case you want to have some more information. Data, knee is the MRI of the knee. DVT image, it's a digital breast tomosynthesis image that we're going to use. That was new from yesterday. And the mammographic presentation, it's a mammographic image that we had already yesterday. So in this case, you have to download the three zip files, okay? And you can start downloading as well the IO, which means input and output. There are two files, that the two first examples, okay? And I don't know, where is it now? Input and output, and then filtering. Well, it was like this. Filtering. There is another one called filter. Okay? You can download all of those. I would suggest to put them in different folders, and we will start with the first example, which is input, output, the DICOM print patient information. Okay? So if I go back to the slides, the idea of the exercises that we're going to do today and tomorrow will be, I assume the Hello World is done, it's working. Okay? Image input, output, we are going to play around with loading DICOM images and being able to check from some particular tags. Okay? Then image input output, let's say 2, it's for reading and writing different types of images. Okay? If we have time, we will do basic filtering today. So applying one of the filterings to one of the images to remove noise, to enhance edges and different things. And I guess that will be for tomorrow to do some image segmentation. Okay? So, just a reminder of what we will need. Not many things. Just to compile anything, you need a CMake list. On purpose, I didn't provide all the CMake lists, so you just copy from the Hello World, you modify a little bit, and you have your CMake list, for instance, for the first exercise of input-output, okay? Should not be that difficult. And then you have the CXX file, you can call it whatever you want, that it will contain your source code, okay? So far, so good? No questions? No? So the first exercise, and I want now that it's going to be probably more participative, these lectures, compared especially from yesterday. I'll go around, and if you have any problems, it's turning more in a lab session than in like a tutorial, okay? So the idea is that you take the DICOM print patient information CXX, you first obviously open the file, trying to understand what it's doing, okay? The idea is to want to read the DICOM mammography and print image tags. You know what DICOM? I guess you do. Yeah? You know that DICOM has different tags? Yes? Something like, for instance, here, the 028030 will refer to, to specific information in the DICOM header, okay? So you'll see that it's already, in this example, you already can check some of the tags, okay? So the first thing you have to do is compile and show that it works properly, and then add some modifications, very small ones, that I would like you to print the pixel spacing tag and the bits allocated tag to see that it makes sense or not. Then you have to modify the code accordingly to load the 3D image and check the spacing in the Z direction, the slice thickness, and which is sometimes is in the slice thickness part. Tag, 1850, but if you don't find this information, maybe it's in another tag, which is 1888. Okay? That's the idea of this first exercise. Yeah? Just one last mention about the data. Okay? For this is good. You remember that I was suggesting to use ITK Snap, so if you can use it to, let's separate what is the data and what is the coding that we are going to use, okay? So one of the things is, it's the mammography image that we're going to use, okay? So you'll see that you have, one of the images are this, okay? ITK Snap is also good to do many things, segmentations and all these things. You'll learn about this, if not during this winter school, I'm sure during the second and third semesters. You can have information about the image, okay? How many pixels, the voxel spacing, and so on and so forth. And also you can check for metadata, which is the header of the DICOM. Okay? Many information can be found in here. Okay? So this is one of the images we are going to use. The X-ray mammography image. We have another one which is called the DVT image, which is also a mammography, but it's a 3D image. Okay? It's a pseudo 3D image where you can see different slices of the images. Okay? Now you can see it. All right? This is can make it larger. Okay, this is another image that we're going to use. Yeah, thank you. Which is a DICOM image, but is instead of 2D is 3D. Okay. And then the last one I already showed you yesterday. It's the knee image. Okay. We'll see if we can use that as well. It's a knee, an MRI of the knee, so we have this information. Okay. Regarding the MRI of the knee, and probably not for today, but for tomorrow, we will be able to do some segmentation on that, hopefully. And the idea will be to have, I know it's not going to be as good as this, probably, okay, but to provide an algorithm to be able to segment you'll see better like this, the knee image, okay? Ideally, well, this is part of a complex problem where we segment the two bones, but also we want to segment the cartilage part, okay, which is probably the most challenging part here. And I'm not asking for the cartilage, but we could do some segmentation of the bones, okay? So in that sense, if you are able to segment the bones, you are able to do something like this, okay? So I can show you 3D volume of the image, of the segmented volumes, okay, which is quite nice and fancy. All right, so this is the data. It's some 3 images, 2 breast imaging, X-ray and mammography and DVT, and 1 MRI of the knee. Okay? So, well, my first suggestion will be to start with, I put back the first exercise, which is the input-output, and the idea is to load the mammographic image and play around with the DICOM headers. Okay, be able to run it. I don't know if you know about how to pass parameters to an executable file in C. You know that you put the name of the executable, but then you can put any arguments that you want to pass to the program. Let's say if you want to load one image, you're looking very strange to me. Should I comment something about this? Okay. So if I load, I'm not going to do the exercise for you, but I can comment the source code of the first exercise, which is this one, input, output, print DICOM information. Okay? This is the source code. You see lots of comments because this is from the software guide. So, as I said yesterday, some of those comments go directly to the LaTeX. Yeah?
Could you help us with CMake file?
See if I could help? How to...
Like for example, how...
Yeah. The CMake file... So that's what you have. If you go to the hello world... Yeah? This is the hello world CMake file. True? Okay? So one thing I can do, and you'll find it in the Google, because I will write there, is, okay, let's use the same one, okay? And I'm going to go into input output, and I'm going to paste it here, CMake list. Okay? Now it's a CMake list which is inside the input output folder. Okay? So now I can call this input output, just to make it more meaningful if you want. Alright? This will be the same. Yeah? This will also be the same, because we have to find the package ITK and use the ITK. We can start putting lines. Sorry, this is 95. It was a telephone number. Add executable. Here will be the name of the executable that we want to use. The first exercise will be, well, let's check the name. Yeah, if you go here, image, reader, cast, right. So I can go here, copy and paste, because that's a C++. And when do we have to link it, we'll do it like this. Yeah? So, in other words, I changed hello world to something else. Okay?
If you want to add should we have like target link?
Yes, if it's another executable, a separate file that similar to what we are going to do in the second exercise, so 2 files that will generate an executable in the same folder, we would add here as many lines as needed. Okay? Sorry, it was not this one. It was DICOM, no? This is the second exercise. Okay? So, if we do it step by step, that will be what I wanted to do. Okay? It's quite an annoying name, so you could do it shorter if you want. Okay? But what it needs to be in the correct name as the file is this, the CXX reference to the file. Okay.
For the DICOM file, with the data knee or the other one?
Sorry? For the DICOM?
Yeah, which folder or file we need to use? The knee, the MRI for the knee? Or?
No, we're going to use the mammography. The mammography, the mammography file, which is mammography presentation DCM. Okay? Don't worry if you have any troubles or something, I'll come around and we'll fix them. Okay? So now I generate the CMake. Make sure you save that. I go back to the, well, not back because we're not there. I go to the CMake, the software. I choose the folder where we have this input-output. Yeah? As a source code. Remember, for where to put the binaries, change it or add a /bin. I used to add a /bin. You can do whatever you want. But don't join the two, the source code and the bin files, because it's going to be a bit messy. You can type configure. Doesn't take very long. And then you click on generate. Once you click on generate, we go back to the folder, and if everything goes as planned, you should have a bin folder there with a solution if you're using Visual C, which is called IOSLN, which is the name of the project. Okay? I click that. In this DICOM print, you can set as a startup project, and you can check the source code. Can make it larger. Yeah? And then you can try to build a solution if it works. Then you have to then check that you have 2 succeeded, in my case 2 succeeded, 0 failed, up to date, 1 escape. Well, the important bit is not to have any failed thing. Okay? Okay, so if compilation was okay, then with a command line, I prefer to use command line, I go to the folder, okay, I go, if you use debug, to the debug folder, it really is, and you'll find this DICOM print patient information, okay? So I can run this program because it's an executable, it's an exe file. Okay? If I run it, it will tell me DICOM prime information, DICOM file. That means that it's when I run it, it expects another thing to go with this call. Okay? The file name to open. Okay? Because it's a command line program. That the one you generate, you generate the executable, but then you pass the parameters as separated by the space, you separated parameters, strings. Okay? So if I type diffs, obviously it will generate an error because this file doesn't exist, the file name.dcm, sorry. No such file or directory. Okay? But if I search for my DCM, which is somewhere very far from here, and I think it's somewhere here. No, not so much. What's the name? Are you lost already?
Yes.
That's good. So I just want to show you how to execute this. I put the name. Well, there's a lot of things here, but this is only the name of the executable. Okay? And then this is where the, whoops, it's gone. This is where my data, my image is. Okay? All this is backslashes because I go folder down. Okay? So, it's not there. No. Oh, you didn't tell me that. I had to steal this file name thing. Okay? So now it works. Now it shows me some information about the icon file. Okay? So now this is executing what we tell him to execute at the program. I know there's a lot of things going on and lots of sources of possible errors. Okay? That's why I'll stop here talking, let's say, and I'll go around and check with everybody that could have a problem. Okay, but the idea is to run this thing, make it sure that it runs and that you understand what it's doing as well. So it's not only a matter of running it, it's a matter of understanding how it's done. Okay, let me just, before helping you, let's say individually, let's see what is the source code doing. Okay, you know it's C++, it's a main, yeah? And it has some parameters sometimes, okay? These parameters of the main is where we put the parameters when we call it. If I put file name, this file name will come here in this arguments v, what it's called, okay? Yeah? So first thing, if you want to be a good programmer, let's say, and if you expect that people is going to use your program with a number of parameters, okay? You probably don't want the program to execute if the parameters are not provided by the user. In other words, I don't want the program to run if I don't enter the file name, because there's no point of running the program without the file name. Okay? So you could check how many parameters the user is entering when calling my program. And this is given by this number. It's an integer number that's also here. Okay, and it's saying, okay, if the number of parameters is less than 2, I will print this error message. You have to use my program and provide me an icon file. And then I exit failure, so I stop the program here. Yeah? Does it make sense, those two lines? Yeah? So if the program goes at this type def, sheet, whatever, that means that the user at least has provided 3 parameters. So it has provided at least a file name. Okay? So we have to trust the user and assume that the file name is correct and it can be found. Okay? There could be other checkings if the file exists, etc., etc. It can be as complicated as you want. Okay? But this is the easiest, let's say, the less complicated error checking. Okay, so we start saying, okay, you remember type def from yesterday? Yeah. So we're going to say that our pixels are of type signed short. Okay. Signed short means sign means that it has negative and positive numbers, and short means that it's not a character; it's twice the size of an integer. Okay. And dimension is an unsigned in because you cannot have negative dimensions, and it's dimension 2. So that means that we have an image of 2 dimensions. So far so good? Yes? This is a const, okay, but we could also do a type def if you want, etc., etc. Okay? So then we are going to work with images. Okay? Again, another type def. Type def the image in ITK of the pixel type and the dimension that we want to use. Yeah? Those two things are defined before in the previous lines. And we call this as a kind of a new type, image type. You can call it whatever you want. Okay? This is not declaring a variable yet. It's just saying, I'm going to have some type, new type, integer, chars, longs, etc., etc. Now we're going to have image type. Okay? And then because I need to read an image, I'm going to declare a new type def. I will call it reader type. Okay? Which is going to be reading. So this is the class or the object to read, in ITK to read images. And obviously I have to read images. So I put image type here, which I'm going to be using the images that I just declared. How does it sound so far? Strange? A lot? Okay. Let me go through it and then we can cry together. Leave this out, for instance, and then I'll start putting parameters to the reader, to the thing that is going to read my image. Okay? I have to have the argument that the parameter I pass, which is the file name. Yeah? So he needs to know where to read the image from. So this will be with this method, set file name, the parameter that I pass, file name.csm, mammography, etc., etc. Okay? This is argument 1. It's linked to whatever I put here. In this case, this one. Yeah? If I put argument 2, whatever it is, it will be argument 2. It can have as many arguments as you want, this program. This will be argument 1, argument 2, argument 3, so on and so forth. Okay? Then very easy. It will read the image. Yeah? You remember that I said update executes the things. Okay? So update will read the image. We're not writing the image anywhere now. You just want to get information from the image. So that's, let's say, you do update at the last step of your data network, let's say, of the ITK. Okay? It's between try and catch because we are good programmers and we want to, if there's any problem, we want to just give the error. Like, for instance, that the file name doesn't exist. That's an error. Okay? And then, this is, I guess, easy in the sense that it's using a function called find DICOM tag, this tag, from the DICOM, let's say the DICOM object, one DICOM object. Okay, so I'm going to find the patient name, the patient ID, the patient sex, age, study date, modality, manufacturer, institution, and model. How do I know that? Because I should know the name of the tag in the DICOM file. Okay, and because I want to print them, I will do, this is kind of print, standard cout, patient name, then the variable, new line, patient ID, patient sex, age, study date, modality, manufacturer, institution, model. Yeah? So when I run the program, if I remove this thing, it's doing this, loads the image, okay? And then patient name, and you say, this is quite strange, okay? This is probably the meaningful one, not for you probably now. But MG means mammography, because it's a mammography image. LORAD, it's the system that it's acquired from, and this is the model of the system. So all this information is inside your image. You don't see patient name, ID, sex, and all this information because most of the time this data is patient sensitive or it's personal, so we tend to remove it at some point. At least for sure the patient name and patient ID. We put different numbers. Okay? Patient sex or patient age, you can leave that as long as the other information is removed. Okay? You'll see with the other DVD image that you can load and see how is it going. Okay? So, how is it You understand everything? Okay, so the idea of this first thing will be to understand what we are doing, to run the program with the parameters that you have, okay, and see that it's doing what it's expected to do, okay, which is now printing the tags. What I'm suggesting here is, okay, you have to use this. You have to read the icon mammography in the image tag, so see that it compiles and runs properly. And then I want you to add two other tags, which is the 2830 and the 2800, which is the pixel spacing tag and the bits allocated tag. And I want you to show this into the screen along with the other information. Okay? After you do this, I want to load the 3D image, a DBT mammography image, and see if it works or not. And I want you to add another tag, which is the spacing between the slices, because now you have a 3D image. It might be some space between the slices. Okay? So also want to know this information. Are you familiar with pixel spacing? More or less means no. Pixel spacing, slice thickness, and all these things? No? Should I comment something about this? Yes? Okay. Oops. So, you know what the pixel is? My voice was better like this. Hello. What is a pixel? I guess you're used to pixels, no? When you load, what is a pixel? It's this picture element. Okay? When you load medical data, all the information, and also that the non-medical is the same, okay? All information comes from a sensor, no? That it captures some physical quantity, like the X-rays, attenuation, the ultrasound, impedance, etc., etc. Okay? So at the end there are sensors. In a camera as well, in the camera of the mobile, you have sensors in the CCD camera. Yeah? So you have one pixel next to each other. So those pixels physically have a size. Yeah? I'm sorry, but they have a size. Okay? So between one pixel and the other one, there is some physical distance. Yeah? Everything is, even if it's very, very small and you have your very fancy camera with 16 megapixels, whatever, these 16 megapixels then means that one is next to each other, so that takes some space. Okay? So this would be, for instance, your spacing. And if we are talking between X and Y as a convention, this will be the spacing in X. Okay? And it's given in what? Meters, for instance. Okay? Kilometers. Or normally in that icon in tags are in millimeters. Okay? So you can check. That's what I am asking you. But it's not here, obviously, because that's what you need to provide. I'm asking you what is this spacing in the image that I'm providing. Okay? And I'm also asking what is this spacing in Y. Okay? Because that's really important when you do some image processing in the medical images. Okay? And this is a 2D image. Have you worked with 3D images? MRIs and all these things? Yes. Well, a 3D image is nothing more than you go and you say, okay, now I have voxels, which is a fancy name to call a 3D pixel. Okay? And you have voxels. So that means you have something, because physically as well, it has a size. So it has a size now, not only in X and Y, but also in Z. True? Okay? And because you have several slices of this image, you have several of those. So you have another one, let's say if I'm going into this direction, very bad at drawing. that will be one pixel or one voxel if you want. If we use the center, that will be another voxel. Yeah? The same x and y dimensions, but a different z. Yeah? So any reference that you use now with the voxel or a pixel that you were used to x and y, we will add a new one which is x and y and z. And it's not more complicated than this. Instead of a 2D matrix, it will be a 3D matrix. That's it. Okay? Yeah? Alright, so the idea of all these images is that you need to know what are the physical size of the pixels. And you will say, why? Can I just use x and y and z and that's it? No, you cannot. Because most of the time what happens is that the x and y and z dimensions are not the same. Okay? In other words, what it's called is they are not isotropic. Isotropic means same size in all directions. Most of the time what happens, for instance, typically in an MRI machine, you have a size 0.6, 0.6, 2.5. This is size in X, size in Y, size in Z. Yeah? Because physically the scanner in the Z dimension where the patient is lying, it's larger than in the in-plane resolution. And there's nothing you can do about it. Okay? But you need to know what is this in order to, when you provide or you do some processing in the image. Okay? Why is that? Because imagine that you have those two pixels, this pixel and this pixel, okay, are a very important lesion in your brain, let's say. Okay? And you need to tell the doctor that your fancy program that it's able to detect those lesions, okay? You need to tell the doctor where are they, okay? And you need to tell the doctor what are their size, because depending on the size, you can have an illness or not, or you can be in different stages of the illness. Okay? So if you go to the doctor and you say, okay, it's in coordinates 2, 4, 2 to 4, let's say, and it will say 2 to 4 what? Millimeters? 2 to 4? It's not meaningful for you. Okay? So the first thing you need to be aware is that doctors and everything is going to be related to physical coordinates. Okay? And to relate pixels to physical coordinates, you need to know this size of things. Okay? What I'm saying all this is because one of the questions I ask is know this size of things. Okay? Because let's imagine that you have to tell the radiologist these two lesions is 1 milliliter lesions. Yeah? And this is very small. Or it's 3 centimeters lesions. Okay, which in the protocol that means really a severe illness and you have to really go into surgery, etc. Okay? So imagine that different scanners have different sizes. That can happen as well. So if different scanners have different sizes, you cannot rely on giving information on pixels. You have to go always into the physical coordinates, the physical world, let's say. Okay? Did I convince you? Yes? More or less? Okay, so what I would like to know is this pixel size from the mammographic image at the beginning. Okay? That's the first exercise. Then we'll do the second part, which is to modify the code to load the 3D image and check the spacing in the Z direction. Okay? So, I think I'll stop recording. Okay, so third and last session of the ITK. I'm recording, sorry. I've been told to. It's going to be short anyway. So we are doing exercises since yesterday, okay? We did this out. I updated these slides. Just a reminder that we're working with DICOM mammography and DVT files. One is 2D and the other one is 3D. and knee MRI data, which is 3D. I've included in the folder, if I click on that, and obviously it's not going to work. You'll see a new inside, well, in here actually. You'll see one called slice PNG. Okay. I have added this as slice PNG. Let me close that. To make things open. I've added this as slice PNG because it's a 2D slice of the central volume of the knee. Okay. This is in order to easy a little bit the segmentation exercise that we're going to do at the end, okay, because it's easy to test with the 2D slice and then try to do the whole 3D volume, okay. Easy in terms of selecting parameters, easy in terms of computational time, etc., etc. Okay, so this, if you download this, you'll see that is only one slice of the central volume, okay, so you can use that to test the algorithms, okay? But the rest is okay. It's the same. Inside, we did input-output. Inside filtering, you have filter, which is the following exercise that we're going to use. And inside segmentation, you have another called filter, but it's a segmentation algorithm, okay? So those are the new files that you are going to find. So if I go back here, just I commented the data. The examples is what we said. We did the image input-output, reading icon tags, and reading and writing images. Now, today we're going to do basic filtering. Okay? So how to use filters, and you'll see that the filters work more or less the same for all of them. And then we'll do image segmentation. Okay? That image segmentation works similarly as a filter. So you have an input image, you do whatever processing is doing the filtering or the segmentation algorithm, and then provides an output. Okay? So this is already done. Image input output, filtering. You'll see an example in the filter folder. And the aim of this exercise is to test the curvature flow filter with the mammographic image and knee 3D images. Okay? Well, you see one is 2D image, the other one is a 3D. You can start testing with a 2D knee if you want. Okay, I'm saying compare computational times in the sense that you'll see that it takes much longer if you use the 3D image compared to the 2D image. And also if you compile for debug or release, you'll see a large difference as well. Okay, if you only compile for one, then you can compare to your neighbors or something like this if they have different. And you'll see there's a large difference. Then once you understand the filter, the same idea applies for everything. So you have to look at the code, understand what it's doing. And then I ask you to do a small change, which is to replace the curvature flow filter with the gradient anisotropic image filter. Okay? And those may sound very strange names. Okay? If they sound strange, you can go and look up on the web what are they doing. Okay? I could explain you, but I think it's better you to get used to look for information on the web, because there are hundreds and thousands of different filters in the ITK, so you are not supposed to know all of them. Okay? So once you want to do something, that you look for the name, you look what the class is doing, the methods that it has, the parameters, etc., etc. Okay? So one of the questions I ask is, what do the filters do? All those two filters. Okay, you'll have an input, you have an output image, and you'll see the effects of this. Is it clear? Yeah. This is the first exercise of today, filtering. So you have to do the make files, you have to compile, etc., etc., as we did. This is also part of the practice, so you get used to this. Okay, and the final part of the exercises will be segmentation. Okay, you'll see a filter.cxx inside the segmentation folder. And contains a segmentation algorithm or segmentation code. using an algorithm known as watershed segmentation. Do you know what watershed segmentation? Nothing? No? So search for it. That's what I say there. Okay? Again, there are several implementations of segmentation algorithms, and the aim today is not to explain, as I said, methods of image analysis, but you can search a little bit how does it work and what are the parameters that they have. Okay? MATLAB has an implementation, and it's quite nice the way it explains. It's very visually well explained. So if you search for watershed, you'll see the first or two entries in Google. It will be quite clear. Okay? So the idea is to execute the filter using a 2D slice, the slice I was talking about the knee, and then the full 3D knee volume. Okay? Again, compare computational times between 2D images and 3D images. You'll see hopefully a large difference. Okay? And then you'll see that the results that you will have will be looking something like this for a slice. Okay? If you use the filter as such, the one I'm providing you, it's going to provide an image like this, which is not a very good segmentation, I would say, because you don't see many of the structures there. Yeah? So one of the changes to achieve something like this, which is much better, yeah, you see that if we are interested in segmenting the bones, segmentation is quite good, yeah, is because the watershed needs as an input not the intensity image, but the gradient image. Okay, because it's important to find the edges, not the intensities, not the value, absolute values. So basically, what we have to do is to put one filter in front of the input of the watershed. And this filter is the gradient magnitude filter. Okay? Does it make sense?
Yes.
Yeah? So add a gradient magnitude image filter before the input of the watershed image filter and use the gradient, this name, okay? But this name is the name in ITK of the gradient filter, okay? With this change, the watershed will create in a homogeneous region simultaneously. What it means is that, well, we're going to have a better segmentation than the one we had before. Okay? So once you do this modification, you can work with the 2D slice and see what are the results that you have. And once you have in 2D good result, you can then try the parameters in 3D. You'll see that watershed has two parameters. I didn't put the values of the parameters explicitly, okay? I want you to find out a little bit. If we are running short on time, then I will tell you the parameters, and that's it. Okay? Any questions? No? So far, so good? Okay, so I think that's it. If we do those two exercises, you can be happy, and I'll be happy as well. Okay? So let's start.